This ideal neuron enclosed by a lipid bilayer illustrates how we can flip the membrane potential by changing its ionic permeability. Ionic permeability changes when ion channels through the membrane open and close. This helps explain the phases of a neuron's action potential. At present, potassium is more concentrated inside the cell and sodium is more concentrated outside. The lipid membrane contains several closed sodium channels and 2 open potassium channels. As a consequence, potassium conductance exceeds sodium conductance. Free potassium movement across the membrane allows potassium to reach its equilibrium potential and establishes the cell's membrane potential at negative 80 millivolts. This represents the resting membrane potential. When the sodium channels are suddenly opened, sodium ions rush into the cell. At this point, sodium conductance exceeds potassium conductance. Accordingly, the membrane potential becomes more positive as it approaches the equilibrium potential for sodium. This change represents the rising phase of the action potential. Now, when we close the sodium channels, the positive charge that has accumulated inside the cell provides the driving force to push potassium ions out through their open channel. Now, potassium conductance exceeds sodium conductance. Potassium efflux takes the membrane potential back toward the equilibrium potential for potassium. This represents the falling phase of the action potential. Finally, the resting state is restored. Potassium conductance is greater than sodium conductance, and the membrane potential equals the potassium equilibrium potential.